Oh, one thing that bugged me, like about these recordings, like I just had my other class, 721, and so I do the same thing I'm doing here, where I'm turning a board and recording at. And so I looked at the video. It's like, this isn't great quality. They're capturing the writing on the board. So actually, now I think about it, I think it looked better in this room, but for that class, I can't be in this room because there's another class. Well, I'll see. Well, I guess you didn't show up not too long ago, right?
What?
You showed up not too long ago, right? Because
yeah.
a previous class that's in here, I guess that ends at 3:45. So, because I'm not sure if they're still in this room. Because if they're not, then I'd much rather have 721 be back in here.
Yeah.
I feel like the videos are useless if they can't see, they can't really read the writing on the board.
Well, maybe they could. Well, no, you're saying the other classes during the.
Well, yeah, but they haven't been here lately. I wonder if they changed.
They might.
I'm gonna have to find out because yeah. Alrighty. Yeah, because I was all set to have that class in here first day. Well, I wasn't. I was virtual first day, but then they're like, "No, we have class in here." I was like, "Oh, well, fine then." So I don't know. Yeah, because I looked at the video for this class and it looked better. So.
Well, maybe they're gone now. I don't know.
Yeah, well, I'm gonna find out, dang it, because I don't really like that room much. Okay, now, sorry to say, I'm actually gonna give you some homework this time. All right. Well, because I've covered things for a single equation. Now, a real goal for this semester is to handle systems of ODEs. So that'll be the next thing. But before we go to that, working with a case of a single equation, we'll set the stage for what I have you do for a system. So once again, to recap, all right, so for a linear first order ODE, so y prime is equal to some coefficient p of t times y plus some other function q of t, and then we'll have a initial condition y of 0 is y naught. And I guess if I wanted to be super general, I could say y of t naught equals y naught, but then just do a change of variable in t. So we'll just have the origin at 0. So what I worked up to last time was a general explicit solution formula for this problem. So I'll just revisit that. So we have e to the minus integral of, integral of from 0 to t with ds y naught plus integral from 0 to t e to the integral from s to t of p of z dz times q of s ds. Okay. Now, eventually, when we get to higher order DEs, we're going to focus on the case where the coefficients, like P and Q in this case, coefficients are constant. So that'll be dealing with systems of ODEs where whatever coefficients are constant. So, really the only coefficient we have in this case is P. So assuming that that's a constant. So I'm going to specialize this formula a lot less messy in that case. So yt becomes, so now the integral of these integrals will just be equal to p times the difference of the limits So we just have e to the pt, y naught, plus integral from 0 to t, e to the p times the difference of a limit, so that'll be p times t minus s, q of s ds. So a bit more digestible. Okay. So now, so now what I'm going to do is I'm going to work through an example. So I need to choose a specific function for q. Let's see. All right. So I'll let p be equal to, say, -2. And then I'll choose q of t equal to t. So now the ODE I'm solving is y prime is equal to -2y plus t. Okay, so that'll be my initial condition. So assuming that y naught is equal to 1. Okay. So now I want to go ahead and apply the solution formula. So normally if you were presented this problem in the first course on ODEs, you'd apply whatever integrating factor technique to this, like you'd actually compute the integrating factor. So here I'm cutting out the middleman to an extent. We're just going to jump straight to this. So if y'all had presented this formula, you could have memorized that and just written it out. Although what we will see, if I do write this out, is the initial condition is easily taken care of. I have a 1 here. But also in a DE class, if you're given a problem like this, an initial condition, you have to do a bit of algebra to account for initial condition. Like you'd have a general solution, and then you plug in the initial condition because you have some arbitrary constant in there, and you have to solve for the arbitrary constant, doing whatever algebra. No algebra required here, provided you memorize this formula. So, yeah. Okay, so then I have e to the -2 t minus s times s ds. So this is a solution. But what you probably do in a class like that, you then have to finish the job by working out the dang integral. So let's take a look at that. So what I want to do first is see if there's anything I can factor out, because anything that doesn't depend, any factor that doesn't depend on s, I can factor out. So because this is equal to e to the -2t times e to the -2 times -s, so that's e to the 2s.
So you can factor out that e to the -2t.
Yeah, so I'll go ahead and do that. And now I have the integral from 0 to t of s e to the 2s. Okay.
What? Oh, no, never mind. It's from the s at the end. I was confused.
Yes, yeah, because it's customary to write them here.
Yeah, well, I just didn't see that.
Okay, yeah.
I was very confused. Okay.
Okay. Now, so let's focus on the evaluation of that. What do we have to use?
Oh, we could. u sub, right? Or, but can we just divide by the 2 and then?
If that S wasn't there, we could do that.
Yeah.
But what's the integration technique that we need to use to take the S into account?
Is it u sub? Is it not u sub?
It's not U sub.
I forgot.
Oh, I think it's worse than U sub.
Um,
Anyone from a virtual peanut
it's
gallery?
not the UV, the Y, it's not any formula, okay.
Oh, what?
Well, I was thinking about the UV, but
Keep going.
so UV substitution.
Oh.
Or U,
Oh, U substitution is not, but
yeah. Not about parts, is it?
what?
No, I don't know.
No, no,
I would say
tell me.
integration by parts.
Yes.
Oh, okay.
Okay. Yeah. Don't hesitate. Just put it out there.
Oh, no, it's fine. I just,
Okay.
I hate integration by parts, but yes.
Yeah. Well, you're gonna hate this homework then.
Yeah.
Okay. So our integration parts we have U, V, du, dv.
Oh, no, that's fine. What am I thinking about?
Oh, partial
Which
fractions.
one were you, partial fractions?
Yeah.
That's what I hate.
Yeah, we're not gonna do that. So, okay.
That's what I meant by UV, not the.
Oh, okay.
DV.
So, when you said UV, you meant this?
Yeah, I was gonna say UV
Yeah.
substitute. I was
Yeah,
like,
that's
that's name.
okay.
Yeah, it's all good. I'm mixing
Okay.
stuff up.
So U would be S, then du is ds, and then dv is e to the 2s ds, and v would be 1/2 e to the 2s. So those are the pieces for our integration by parts. So I'm going to focus only on this. So what we get is u times v, so that's 1/2 s e to the 2s. And then we have minus the integral of v du. So we have a 1/2 out front, and then we just have e to the 2s ds. And that works out nicely enough. Oh, I don't want to forget about my limits. Okay. This is a definite integral that we're doing. So for remaining integral, e to the 2s, now we can do what you said earlier. You divide by the coefficient of s. So now I have 1/2 s e to the 2s minus 1/4 e to the 2s with limits 0 and t. Now, what I'm going to do is, in my head, take the derivative of what I just wrote there, just to make dang sure that it's correct. Okay, so I think just 1/2 to the 2s minus 1. Yes, okay. So, a question about any of that? Actually, what I can do now is plug in the limits. Okay. So that would be 1/2 t e to the 2t minus 1/4 e to the 2t. That's when I plug in t. And then when I plug in 0, well, that part will be 0. And then e to the 0 will be 1 over here. So I subtract off.
Would it be an addition? Would you subtract?
Yes, it would be. Good catch there. Okay. In fact, when I plug in t equals 0, I should get 0. So yes, in this case, I do. Okay. So now the integral has been completely evaluated. So now I can take that and substitute that back in here with the rest of the rest of the solution formula. Okay, so okay, I think I better do this on a fresh board. So I'll take a picture. If anyone has any questions before I erase, let me know.
That was UV minus the interval of VDU. That's the.
Yes, that's the integration by parts formula.
Yeah, just making sure.
Okay. All right. Let's see. Before I erase all that, I'll incorporate it over here. Y is equal to, okay, so e to the minus 2t that I had earlier, plus e to the minus 2t times that whole integral that was 1/2 t e to the 2t minus 1/4 e to the 2t plus 1/4. Okay. So now to simplify this as much as I can. So I guess. So e to the minus 2t will cancel with the e to the 2t's in here. Okay. Now, what I want to check is if I substitute t equal to 0, then yes, I will get 1 because all of this would cancel, would go away when I said t equals 0. Okay, so this is our solution. Now, actually, I can condense it a little bit. Well, so I'm going to label these two pieces. I could combine these like terms, but I'm not going to in this case. I want to talk about these two pieces separately. I'm going to label this y sub h of t, and this is y sub p of t. Now, the names of these pieces, this is called the homogeneous solution. And yp of t, I'm calling a particular solution. Okay. Now, solution of what exactly? I need to make that clear. YH of t is a homogeneous solution of the ODE. Y prime is equal to minus 2y. So, any solution of y prime equals minus 2y is this exponential times a constant. Okay. This part is a particular solution of the ODE we started. Y prime is equal to minus 2y plus t. So, all solutions of this problem have this form. It's a homogeneous solution plus a particular solution. So, actually, I can write down what this more explicitly. Okay. General solution of y prime is minus 2y plus t is an arbitrary constant times a homogeneous solution plus a particular solution. Because, so to verify this, y prime, well, that's equal to constant times yh plus yp prime. But by the linearity of differentiation, and I have that. Now, yh prime is minus 2yh. This solves that ODE. And yp prime is equal to minus 2yp plus t. So now I can group these terms like that. So anything involving y, group those terms together and everything else is written off to the side. But that's y. So it really does satisfy the ODE. And if you had an initial condition, you would enforce the initial condition to find the value of this constant. So, if I have y of 0 equals y naught, then I have cyh of 0 plus yp of 0 equals y naught. So you have to solve this equation for C. Now, in my example, I came up with a homogeneous solution so that this is equal, this part is equal to 1. And for a particular solution, I plug in 0 equals 0. So C turned out to be the initial value, but that's not always going to be the case. I wrote the solution formula to make those things happen, like the integral being from 0 to t made that happen. Okay. All right. Now, the thing I want to focus on now, well, first, any questions about anything I've done up to this point? Is, okay. All right, take a picture of this, and I want to erase just the verified part, keep the other stuff. Now, if you look at the particular solution, we're solving this ODE, constant times y plus qt. So back to the general form of the ODE, but with p equal minus 2 and q of t equal to t, then the particular solution that we got is a linear combination of certain functions. And what I want to focus on here is, what are those functions? Because we had three terms altogether over here. So if we ignore the constant factors, what we got was a linear combination of one, so there's a constant term, and there's a linear term, so we have t. And then we have e to the minus 2t. But the thing is, e to the minus 2t, that's a solution of the homogeneous equation. So we're actually going to have a term like that anyway. So what I'm most interested in is terms that are not homogeneous solutions. So this is this 1 and this t. So in qt happened to be a linear function. The particular solution also included a linear function. And then a homogeneous solution, but we already had that. So what I give you homework problems to explore is, for certain functions that play the role of q of t, what functions do you get that describe your particular solution? So now that I've stepped through one example here, where I went to trouble evaluating the integral and all that, what I want you guys to do for homework is do the same with other choices for q.
So this one ended with a linear combination. Is it always? It's always going to be a linear combination.
It's always going to be a linear combination of certain functions.
We're comparing the linear combination from homework to what we're doing now and seeing.
Yes. So for each given q, and I'm going to list some q here. What functions end up coming out of the integral? Because that's it. That's just it. You're going to evaluate the integral and see, oh, here are functions that you get as part of your linear combination. Okay. Okay. So let's now go ahead and fully describe the problem. Okay. Now, okay. So all right, so we're given this ODE, where you're assuming that p is some constant. Okay. So what is the particular solution which I'll write out the formula for? It's just a part of the solution formula that deals with the integral. Okay. What is a linear combination of? Other than the homogeneous solution, which we already know what that is, that's e to the pt. So in other words, e to the pt itself, you're not going to consider. It's other functions that we want to know about. Okay. So here's the Q of t of interest. So Q of t equals t I've already done. So first, some specific examples like t cubed, t squared, t cubed, and then t to the n. N is a non-negative integer. Okay. And then other functions of interest, e to the at, where a is not equal to p. So that's an important assumption here. And then separately, e to the pt itself. So those cases will play out differently.
Okay, you have e to the pt, but the linear combination part is only for the.
Right, but the thing is, you'll plug that in for q. You'll have e to the ps in here, and then you work out this integral. Something else will pop out.
Okay.
Yeah. Okay. Okay. Actually, the easiest case of all, q is equal to 1. So that's covered by this. Maybe it's good to start with that one. Okay, so okay, and I skipped over t because I already did it. Okay, but the idea is, after you do these few and see a pattern, then you can jump to a conclusion on this one.
Right.
Okay.
So we're gonna weigh up with those first few and then those two cases.
Yeah. And then we'll do cosine of bt, sine of bt, and finally exponentials times cosines and sines. Okay, I'll stop there. Now, evaluating integrals, but I do not care how you evaluate these integrals or what assistance you use to evaluate these integrals. You can use tables of integrals, you can use Wolfram Alpha. I don't care. This is not Cal 2. But just to see what the final result is. What I'm laying the groundwork for is a method for solving higher order equations called the method of undetermined coefficients. And that's for higher order, not so much first order, but when we come to those, this will come in handy for that. Okay. Yeah. Okay. I haven't really thought about how much time to take for this because I kind of don't care. But well, it'll be a while before we need this, or later things I'll do with higher order equations. So I guess what I'll do is like during next class or also Tuesday, just see how you're doing with it, because I just made this up yesterday. So we'll see. It'll be interesting to see how it goes. I don't think anyone will complain if it's too easy, including myself, but I also don't want it to be too outrageous either. So. Oh, whoops, that's a mistake. The exponential should be the same, e to the AT, and then cosine or sine BT.
Okay.
Yeah. Okay. Oh.
Do we care about the n0? I'm not sure t squared t cubed to tm where n is 0 through whatever.
Yeah.
I mean, we just t0, t1, or t to the 0, t to the 1, t to the
Yeah.
2. Okay.
Yeah. Oh, shoot. I did forget something. Well, like, so I got, products of these. I was thinking I also want to have like polynomials times exponentials or, okay. I'll throw in just one more. T e to the AT. So you can see like, okay, how does this one differ from just e to the AT by itself? And then you can probably figure out from there and all the other ones you're doing, well, what if you had, t squared or t cubed e to the AT, what would happen in that case? So.
And you said where p is a constant. Do you want us to just use a general c?
I want you to keep things general, yeah.
Okay.
Yeah, because what this class is really about is developing solution formulas that you just plug whatever particulars of ODE into. Okay. Questions from virtual land?
I'm good for right now, but I know I will eventually have questions.
Okay, I will brace myself for that. So.
I was gonna say that's kind of how I feel too.
Yeah. Alrighty. Well, I had to give you all something to do sometime. And while you got this going on, pretty soon we'll be getting into linear algebra mode on the higher order equations, but okay. Okay, well, it's almost 5, so this is a good stopping point. And then I'll see you all in a half hour.
Thank you.
Yep.
Yeah, obviously completely mixed up my integration technique names.
Okay.